To start with in this section, I just want to remind you about what's called the coordinate plane or the XY coordinate system, or sometimes just called the plane or the Cartesian plane. All these things refer to the same thing, which surely you've seen before in multiple math courses, so no need to go into deep detail about this. But it's just a way of representing the relationship between two variables, commonly called x and y. X on the horizontal axis, y on the vertical axis, but the variables can be given different names. Sometimes they stand for some real-world variables that have some relationship. Sometimes it's just an abstract mathematical relationship. The idea is that we just place two number lines perpendicular to each other. And so x can take on any real number measured along this direction, and y can take on any real number measured along this direction. So if I have a point in the plane, the name of that point, say it's P, and it has coordinates A and B, that just means that we're A units along the x-axis and B units along the y-axis. So this says that when x takes on the value A, y takes on the value B. And just to notate this a bit more, this again is called the x-axis. This is called the y-axis. The point at which they intersect is called the origin. That's the point 0, 0. And in general, we describe a point on the plane as having an x-coordinate and a y-coordinate. So this point has an x-coordinate of A and a y-coordinate of B. And so here's just some examples of points plotted on the plane. So this point, whose name happens to be A, has coordinates 3, 2, meaning that we've gone over 3 units in the x direction and 2 units in the y direction. This point has coordinates -3, -4. We've gone over -3 units in the x direction, right? Negative is the leftward direction, and -4 units, down 4 in the y direction, right? Up is positive, down is negative, right is positive, left is negative. On this page, we're going to take a look at a formula for finding the distance between 2 points in the plane, and also a formula for finding the midpoint of a line segment connecting 2 points in the plane. So let's say we have 2 points in the plane, and I want these to be totally arbitrary. Like, don't try to count how far over and up I've gone. These are 2 points that could be anywhere in the plane. And so I don't want to give them specific numbers. I just want to label them as having x and y coordinates. Although notice the way I've labeled them is a problem, because I've labeled them both as x and both of the second coordinates as y. So this doesn't allow me to distinguish between this letter and this letter. If I want to call them both x, but I want to be able to distinguish between them, that's when we use what are called subscripts. So I'm going to say x sub 1 and x sub 2. And I'm going to do the same thing with the y coordinates, so that I can distinguish between the y coordinates, yet still call both of them y. So unlike exponents, these numbers don't have any mathematical, they're not indicating a mathematical operation. They're just a way of saying that this x is different from this x, and this y is different from this y. All right, so I'm interested in finding a formula for the distance between these points. In other words, the length of that line segment. So let's call that d. And the clever way we go about finding d is to fill in this distance and this distance, and then to recognize d as the hypotenuse of the right triangle that I formed this way. Remember, a right triangle is a triangle that has a 90-degree angle that 2 of the sides meet at, and then the longer diagonal side is called the hypotenuse. And then you probably remember that if we call this side a and we call this side b, then a squared plus b squared is equal to, in this case, d squared. For a hypotenuse, it's often called c, but I've labeled it d for distance. So this squared plus this squared equals this squared, and that allows me to find a formula for this length d. So what I need to do is fill in the lengths of these sides. And so notice that if this point has an x-coordinate of x sub 1, then that means that I can label like this. And so if I'm going from x sub 1 to x sub 2, then it means that this distance must be x sub 2 minus x sub 1. And then similarly, this distance must be y sub 2 minus y sub 1. So this point has a y-coordinate of y sub 2. This point has a y-coordinate of y sub 1. And then this distance is the same as this distance, which is just y2 minus y1. So then the Pythagorean theorem comes in and says that this side squared plus this side squared is equal to this side squared. So x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared equals d squared. And remember, we're trying to find a formula for d. So all I'm going to do at this point, I just want to flip the sides because I'm trying to solve for d, so I want to get it on the left. And then essentially I'm just taking square roots of each side. If d squared is equal to all of this, then d itself is equal to the square root of that whole quantity. And you might think that you can cancel the square roots with these squares, but you can't, because remember that square roots don't distribute over sums. So this gives the formula. That's what I'm going to fill into this box. The distance between these points, x1, y1, and x2, y2, is the square root of the difference of the x-coordinates squared plus the difference of the y-coordinates squared. The formula for the midpoint of the line segment, that one's a little less exciting. This kind of cleverly involves making this triangle and using the Pythagorean theorem. But this one, and again, let's just have a quick picture here to illustrate. Here I'm just going to place these points just in the first quadrant for convenience, but it doesn't matter. This generalizes no matter where these points are located. If I have this line segment, and I want to know what is the midpoint of that line segment, the point halfway in between these points, well, this point, its x-coordinate is just the average of these x-coordinates, and its y-coordinate is just the average of these y-coordinates. And remember that to find an average of two numbers, you just add the numbers and divide by 2. So in symbols, that looks like this. All right, so here's some practice applying these formulas. It says that a pair of points is graphed. We've got these points right there. And I'm asked to find the distance between them and the midpoint of this line segment that joins them. So first, let me label these points. This is the origin right there. This point appears to be left 2, down 3. So that's the point -2, -3. And this point is 1, 2, 3, 4, down 1. So this is the point 4, -1. All right, so the distance between those points then, according to that formula above, I just take the difference of the x-coordinates, so 4 minus -2 squared, plus the difference of the y-coordinates, -1 minus -3 squared. Now you might wonder, how did I know what order to subtract them in? The answer is it doesn't matter. I could have done the other order instead. I could have done -2 minus 4 and -3 minus -1. It doesn't matter what order I subtract them in because I'm squaring it anyway. And you can test that if you take two numbers and you subtract them in either order, if you square the result, you're going to get the same answer regardless. Now we just have to work out the arithmetic. 4 minus -2 is 4 plus 2, which is 6. Squared is 36. Well, let's save that for the next step. Let me just write 6 squared. And here I have -1 minus -3. That's -1 plus 3, which is 2. Squared. Remember, the square root doesn't cancel the squares because square roots don't distribute over sums. I just need to work out what's inside the square root. That's 36 plus 4. That's 40. And so I get the square root of 40, which simplifies to 2 root 10, but you don't need to bother doing that. What I do want you to do, though, is leave it as the square root. You could get a decimal approximation from your calculator, but we don't want approximations unless we're asked for approximations. By default, you should give the exact answer. And so just leave this as the square root of 40, or you can simplify it to 2 root 10 if you wish. All right, the midpoint. That's even easier. I could eyeball it right there, but according to the formula, all we need to do is average the x-coordinates. So add the x-coordinates and divide by 2. and do the same thing for the y coordinates. Negative 2 plus 4 is 2 over 2 is 1. Negative 3 plus negative 1 is negative 4 divided by 2 is negative 2. So there's the midpoint. Now we're going to begin looking at equations in two variables and their graphs. So an equation in two variables is just an equation that expresses a relationship between two quantities, two variables, x and y being the most common letters for two variables that have a relationship in an equation, but of course the letters could be something else. So an example here is y equals x squared plus 1. That just says that the value of the variable y is always the square of the value of the variable x plus 1. So a given point x comma y satisfies the equation if it makes the equation true if I were to substitute these values into the equation. The graph of an equation is the set of all such points that satisfy it. So for example, the point 3 comma 10 satisfies this equation because if I were to plug 3 in for x and 10 in for y, the result would be a true statement because 3 squared is 9 plus 1 is 10. And so 310 satisfies this equation. This isn't the only point. So does, let's see, 1 comma 2 or 0 comma 1. There are infinitely many pairs of x and y values that satisfy the equation. So what the graph of an equation is it's just in the xy coordinate system, you plot all of the points that satisfy the equation, and that shows the relationship among the x and y variables illustrated by this equation. All right, so here's another one. 2x minus y equals 3. This is an equation in two variables. It illustrates some relationship between x and y. And for starters, we're just asked to determine whether the point 0 comma negative 3 is a solution of this equation. So we just plug in 0 for x and y for negative 3 into this equation, and we see if the result is a true statement. One handy notational abbreviation that's often used in math is LHS and RHS. That just stands for left-hand side and right-hand side, because we're so often working with equations, and we just want a convenient way to talk about the left side of an equation and the right side of an equation. So what I'm going to do is take these numbers for x and y, and I'm going to plug them into the left-hand side of the equation and see what I get. Well, 2 times 0 minus, in place of y, I'm plugging in negative 3. I've got a double negative there. That's 0 minus negative 3. That's 3, which is equal to the right-hand side. In other words, when x is 0 and y is negative 3, the left-hand side equals the right-hand side, meaning the equation is satisfied. So that means that the point 0, negative 3 is in fact a solution of the equation. Now I'm going to check negative 2 too. So when x is negative 2 and y is 2, the left-hand side becomes 2 times negative 2 minus 2, which is negative 4 minus 2 is negative 6, which is not equal to the right-hand side, which is 3. So that simply means that negative 2, 2 is not a solution. So what we're now asked to do is just find more points that do satisfy the equation. And just to be clear on the vocab there, when I say that something is a solution of the equation or that something satisfies the equation, those are synonyms. Those are just two different ways of saying the same thing. So this is one point that satisfies the equation. We're just asked to find more of them and to find enough, in fact, that we can confidently sketch the graph. So the easiest way to do that is, let me take this equation and first solve it for y, write what y is in terms of x. So if I just subtract the 2x and then divide by the negative 1, or if I just add the y to this side and subtract the 3 and then flip-flop the sides, either way I get y equals 2x minus 3. And having y expressed in terms of x makes it easier to generate points that satisfy the equation, so I can just pick any x value I like, plug it in, and see what comes out for y. So I'm just going to plug in integer values of x, negative 2, through 4. And if you didn't think to choose those, that's okay. I mean, you can pick your own x coordinates and see which ones spit out y values that fit on the graph. But I happen to know that this is a good set that works because I've already tried this one. So I'm going to take this value of x and plug it in and see what I get for y. 2 times in place of x is -2 minus 3. 2 times -2 is -4 minus 3 is -7. So what that tells me is that the point -2 comma -7 satisfies the equation. I mean, you could check it back in the original if you like, just like I did this one, right? Take -2 for x and -7 for y, plug it into the original equation, and you'll see that it comes out true. The left side matches the right side. All right, when I plug in -1, same deal, 2 times -1 minus 3. That's -2 minus 3 is -5. And so -1, -5 is another point that satisfies the equation. I won't talk through the rest of them in detail. I'll just tell you what comes out. -3, -1, 1, 3, and 5. And I'm going to plot these points. Well, this one falls off the grid, actually, -2, -7. So I could put it down there, or I can just not bother and do these instead. -1, -5. 0, -3. 1, -1. 2, 1. 3, 3. And 4, 5. These points seem to follow a very clear pattern. And I mean, maybe, I don't know, in theory, there could be a point way out here that satisfies the equation, maybe some point in between that randomly doesn't. But it turns out here that the suggested pattern is the right pattern. In other words, not only did these points satisfy the equation, but the x and y coordinates of all of the points in between do, and none of the points outside of here do. We would know that for sure if we knew that the graph of this was in fact a line, which it in fact is. We're going to learn in the next section a criterion for knowing whether the graph of an equation is a line. But for now, you can, I'm sure, confidently take my word for it that the graph of this equation is in fact a line, meaning that all of the points along this line, including the ones with fractional and decimal x and y coordinates, do satisfy the equation, and none of the points outside of it satisfy the equation. So this line is the graph of this equation. We're going to have a look at the graphs of two other equations here. Y equals 3 minus x squared. To generate some points that satisfy the equation, I'm just going to make a table again and use x coordinates -3 through 3. So I plug -3 in. We have to be a bit careful here with the parentheses and order of operations. Y is 3 minus, and then I'm squaring x. Here x is -3. So I need to indicate that I'm subtracting the square of -3. So to communicate that using proper notation, it needs to look like this. To square a negative number, the negative needs to be within parentheses. So this is what I'm evaluating. And these negatives don't cancel because this one is under the influence of the square and this one isn't. So following the order of operations, I need to square the -3 first, and then I subtract the result of that from 3. So that looks like 3 minus, and then when I square -3, I get +9, and then 3 minus 9 is -6. So I get the point -3, -6. I won't go through the rest of these in detail. I'll just tell you what spits out. You plug in -2, out comes -1, and for the rest of these, I get 2, 3, 2, -1, -6. Then I'll plot these points. Here's the origin. So -3, -6. I go left 3 and down 1, 2, 3, 4, 5, 6. -2, -1. -1, 2. 0, 3. 2, 1. And 3, -6. So these points rather clearly do not form a line. In fact, they form a shape that you're probably familiar with as a parabola. The graph ends up looking like this. And we'll learn a whole lot more about parabolas and quadratic equations later in the course. But for now, you can take my word for it that the graph does in fact look like this. All right, here's another one. This one involves absolute values. y equals absolute value of x plus 2. Again, we'll make a table of values. I'm going to use x values. Here I'm skipping by 2s just because, again, I've already tried this out and I was able to tell that by counting by 2s here, this gives me a fuller illustration of what the graph looks like. But don't worry about it if you wouldn't have thought to do these on your own. If you just skip by 1s, as long as you use enough points, you would also be able to confidently tell what the graph looks like. So the skill of picking the right x values is not a skill you're going to have to really learn how to do in this course, especially since we're going to learn much more sophisticated ways of graphing equations throughout the course. This kind of plug and chug and just plotting points and connecting them, we're really not going to be doing that beyond this section anyway. All right, so to plug in -6, that's absolute value of, in place of x, is -6 plus 2. I always need to evaluate within the absolute values first and then apply the absolute values. So -6 plus 2 is -4, and then I'm taking the absolute value of that, which gives me +4. So the point -6, 4 is the solution of this equation. And when I evaluate the rest of these, again, just carefully following the order of operations, my y values are 2, 0, 4, 6, 8. And then I'll plot these points. -6, it's 1, 2, 3, 4, 5, 6, up 4. -4, 2. -2, 0. Did I skip 0? I should have plugged in x equals 0 here. 0 plus 2 is 2. Absolute value of 2 is 2. I'll include that point. So 0, 2, 2, 4, and 6, 8. 4, 6 first. And 6, 8, if I want to go up that far. This isn't quite symmetric, but if I pick some more points in this direction, I would end up getting more points like this. And either at this point already or by plotting a few more points, you should be able to confidently convince yourself that the graph of this forms a V shape. Effectively, what we're getting here is the graph of two different lines. Because remember, the formula for absolute value is technically absolute value of x plus 2 equals x plus 2 if x plus 2 is positive, and it equals negative quantity x plus 2 if x plus 2 is negative. And the graph of both of those, which we'll review in the next section, are lines. And so the graph of this full absolute value equation ends up being two different line segments that meet at a sharp point. And again, we'll study these kinds of graphs later in the course. You don't need to worry for now why the graph looks like this, but hopefully you could discover for yourself that it does just by plotting enough points and connecting them using enough sample points. You can convince yourself that the graph must look like this. Some of the most important points on the graph of any equation are the intercepts. The x-intercepts, of which there could be 0, 1, or more than 1, are the points or points where the graph touches or crosses the x-axis. So for example, if I have a graph that looks like this, I've got the x-axis and the y-axis. The x-intercepts, this one happens to have 3 of them. These are the points where the graph touches the x-axis. Notice what's special about all of these points is their y-coordinates are 0, right? This point, its x-coordinate is some negative number, some small positive number, a larger positive number. But what I can tell for sure is that the y-coordinates of these points has to be 0. So if I had an equation and I wanted to figure out what were the coordinates of the x-intercepts, if I didn't already know what the graph looks like, then I could do that by plugging in y equals 0 and solving for x. Because again, I can tell that each of these points have y-coordinates of 0. So if I want to know what their x-coordinates are, just plug y equals 0 into the equation and solve for x. The y-intercept is vice versa. Here's a graph. And this one happens to have 2 y-intercepts. I've got that point and that point. And notice that these points have x-coordinates of 0, right? Because they're neither left of the y-axis or right of the y-axis. So the points directly on the y-axis have x-coordinates of 0. So if I wanted to know the coordinates of these points, if I had the equation of the graph, I could plug in x equals 0 and solve for y, and that would tell me where those points are located. So we're going to do that for this example here. This is the graph of x squared minus xy plus 3y equals 1. This would be very difficult to graph by hand, but computers are good at graphing complicated equations. This is a computer-generated graph of this equation. All of these points represent all of the pairs of x and y coordinates that make this equation true. So our job is to figure out what are the exact coordinates of these points. Those are the x-intercepts. And the coordinate of this point, that's the y-intercept. So to find the x-intercept, again, we're just going to set y equals 0 and solve for x. So I take this equation, and anywhere I see a y, I just replace it by 0. So this says x squared, x times 0 is 0, 3 times 0 is 0, so that all goes away. I just get x squared equals 1. And the solution to x squared equals 1 is x equals plus or minus 1, meaning that when y equals 0, x is either 1 or negative 1. And so this has two x-intercepts, 1, 0, and negative 1, 0. To find the y-intercept, I just plug in x equals 0 and I solve for y. So I take this equation, and anywhere I see an x, I replace it with a 0. These two terms vanish, and I just get 3y equals 1, which gives y equals 1/3, meaning that when x is 0, y is 1/3. So that is the point 0, 1/3.